Hi, my name is Anand Krishna, and I'm a second year PhD student at the Indian Institute of Science, and I'm going to be presenting a work, Tight Approximation Algorithms for P-mean welfare and Subadditive Valuations. This is joint work with my advisor, Professor Siddharth, Professor Umang from Tata Institute of Fundamental Research, and Rajani, who was at Chennai Mathematical Institute during this work and recently moved to Stony Brook for a PhD. Let's start with an introduction to fair division. Fair division tries to divide resources in an equitable way. It can be used to divide up an estate or a piece of land among heirs. Fair division can also be used to split up assets of a business when a partnership is being dissolved. It can even be used by roommates to divide up the cleaning chores when the cleaning deposit is on the line. Based on the type of resource divided, fair division can be broadly classified into discrete and continuous fair division. In a continuous fair division setting, the item set is divisible in an infinite number of ways, and shares can be increased or decreased by arbitrarily small amounts. Typical examples of continuous fair division involve the division of land, cake, pizza, etc. A fair division is discrete when the item set is made up of objects that are indivisible, like paintings, house, cars, etc. Our focus is on discrete fair division. So let's look at the setting formally. We are given n agents and m indivisible goods. We use m with square brackets to denote the set of items and n with the square brackets to denote the set of agents throughout. Every agent I has a valuation function vi over the subset of items. Then the main question of fair division is how do we divide these resources in a fair and economically efficient manner? Let's take a look at few popular welfare notions. Let A denote an allocation. An allocation is a partition of goods into n disjoint subsets. A common welfare notion is to find an allocation that maximizes the average social welfare, which is just the average of the utilities that each agent has for their bundle. Another notion is to maximize the net social welfare, which is the nth root of the product of utilities of agents for the bundles they have received. Yet another would be to maximize the minimum utility of the bundle received across agents. To parameterize these forms, let's look at writing these in a slightly different way. So, the social welfare function can be written in the following form where the parameter p takes value 1. Similarly, taking the limit at 0 for the modified function would obtain us the net social welfare function. Likewise, taking the limit at negative infinity for the modified function again would get us the min welfare function. So, to generalize, the key takeaway from the previous slide is that we can capture a range of welfare functions using the p-means welfare where p is a parameter. P can take any real value but is only relevant as a welfare measure for p less than or equal to 1. As we have seen, p-mean welfare captures various welfare notions, and if we are able to maximize generally for the p-mean welfare, we can also maximize for all the previous welfare notions. The focus of this talk would be on net social welfare, and it's known to capture a wide variety of fairness properties. It's known that the maximum net social welfare allocation is Pareto optimal, which means that any allocation that increases the utility of an agent must decrease the utility of some other agent. It is envy-free up to one good for additive utilities, and additive utility just means that the value for a bundle is the sum of the values for goods in it. There are multiple connections for net social welfare to equilibria in markets, and it's used in practice in various fair division softwares like Splittit, which has attracted a vast user base over the years. But computing the net social welfare allocation, even for additive utilities, is known to be APX hard, and the best you can hope for are constant factor approximations. So we formulate our problem as follows. Given a fair division instance with m goods, n agents, along with their valuation functions, how do you find an allocation A such that the net social welfare resulting from A is an alpha approximation to the Nash optimal allocation? Here, n star denotes the Nash optimal allocation. To store these valuation functions, we need an exponential space if we are storing value of each subset of goods for all the agents. So we assume that we are given a value oracle which, when given the agent and the bundle, gives back to you the valuation that the agent has for this bundle. One can assume more powerful oracles, but we consider this simple oracle for our purpose. Our focus is on the class of subadditive valuations or complement-free valuations, which is a fairly broad and general class of valuation functions. This class encompasses both additive and submodular functions. These set functions model the natural property of diminishing returns and is generally considered to be the largest class below general monotone utility functions, which is of interest to obtain efficient approximations for various optimization problems. A subadditive valuation function is one which satisfies the constraint that, given any two subsets of the underlying item set, the sum of valuations of the individual bundles is at least that of the union of the bundles for any agent. We make a few standard assumptions on the valuation function V. The valuation functions are assumed to be known publicly since we don't consider strategic agents, and the valuation for the empty set is 0. Also, the valuation function is assumed to be monotonically increasing and therefore non-negative. To look at the previous results, for additive utilities, a 1.45 approximation was given by Berman et al. In 2018. For submodular utilities, we know from Wondrack's results that it's hard to obtain an approximation factor better than 1.58 for this problem. Gerg et al. In 2020 gave an order n log n approximation for submodular utilities. And for subadditive utilities, only an m-n plus 1 approximation was known, which was given by Nguyen and Rote in 2014. So let's take a look at the results that we have. We provide an order and approximation algorithm for maximizing net social welfare under subadditive valuation functions, and note that this beats the previously known order n log n approximation for submodular valuation functions. With minor modifications in the net social welfare algorithm, we extend the order n approximation for p-mean welfare for any p less than or equal to 1. For ease of understanding, this presentation only looks at net social welfare maximization, and similar techniques extend to p-mean welfare maximization as well. Similar results for the upper bounds were independently given by Chowdhury et al., but the techniques we use vary widely from theirs. We also show that the order n approximation is tight by proving that an exponential number of queries would be required to improve this approximation even by an epsilon factor. Our lower bounds also apply to the work by Chowdhury et al. So let's try to develop some intuition on how to tackle this problem. Consider that we have subadditive utilities for all the agents. To get a taste of how we solve this problem, let's start out by considering two extreme cases. First case, where we suppose that all agents have a distinct high-valued good in their Nash optimal bundle. That is, there exists a distinct good Gi whose valuation gives an n approximation to the Nash optimal bundle. And the other extreme case where we assume that all the goods are low valued. That is, no good gives an n approximation to the Nash optimal bundle. We combine both these extreme cases to obtain an n approximation for subadditive utilities. Now let's look at the cases individually. Consider case 1, where we assume that we have to maximize the Nash social welfare when all the agents have a distinct high valued good in their Nash optimal bundle. That is, there is a good which gives a 2n approximation to the Nash optimal bundle for all agents, then the nth root of the product of utilities of these high valued goods gives an n approximation to the optimal Nash bundle. So, performing a max weight matching of goods to agents using the weights as the log of utility for individual goods maximizes the product of utilities of n goods, therefore giving a 2n approximation to the value of Nash optimal bundle. Considering the other extreme case where we suppose that all the goods are small, that is, when none of the goods can fetch a 2n approximation to the Nash optimal bundle, then the moving knife algorithm succeeds in solving the problem. Let's now look at the moving knife procedure and how it works. Suppose that all the goods are small, that is, none of the goods give a 2n approximation to the bundle that we started out with, and the algorithm is very simple. You begin with an empty bundle S and keep adding goods to it until someone calls out, indicating that this bundle has at least a value that is a 2n approximation over the set of goods that we began with. We continue to allocate till no agents remain. The last bundle is allocated to the last person standing. This algorithm guarantees that starting out with small valued goods, the allocation so obtained is a 2n approximation to the value of the set of goods we began with, and the proof of this guarantee uses subadditivity crucially. So combining both these cases together with a simple matching followed by a moving knife procedure fails. We can construct examples to show that the matching step might assign goods in ways that fail to achieve an order n approximation even for additive utilities. We combine the extreme cases by introducing a quantity Li. We define Li to be the minimum value for any set of goods after removing 2n of them from the item set. That is, Li over 2n is the value that each agent is guaranteed to receive in a near proportional allocation even after the removal of any 2n size subset of goods. The reason we introduce Li will be made clear in the next slide. We face the issue that the factor Li cannot be approximated within a linear factor, and we solve this issue by maintaining upper bounds on Li using a guess and check method. For this talk, we proceed by assuming that we can calculate Li exactly. Our key lemma to solve the problem for subadditive utilities is the following. The proof of this lemma uses subadditivity crucially. To stitch the matching part with the moving knife procedure, we use the following lemma. It states that for all agents, either there is a high valued good in the Nash optimal that guarantees an n approximation, or the quantity Li over 2n guarantees the required approximation. This result ensures that a single high valued good, in particular Gi star, which is the max valued good in Ni star, coupled with a 2n approximation to all the low valued goods, that is Li over 2n, is sufficient to ensure a 4n approximation for each agent. Considering the log of the LHS of the stitching lemma as weights of a max weight matching, we get that the product of the weight is a 4n approximation to the optimal Nash social welfare. Since in the second phase, after removing the n matched goods using the moving knife procedure, we know that each agent gets at least an approximation of the small valued goods, and including Li over 2n in the modified weight of the matching is trying to account for that later allocation in the first step itself. So we can proceed by computing a matching pi to maximize the sum of the modified weights. We can then go on to compute the Li values for all the agents and then assign the remaining goods such that its value for each agent is at least Li over 2n. But how do we do this assignment in the last step? Consider the algorithm for the subadditive Nash social welfare problem. The first step is to find a matching pi that maximizes the product of the modified weights. Let us use G1 to denote the goods assigned in the matching step. Now assume that all the goods that remain after the matching are small. That is, no good in the remaining bundle gives a 2n approximation to the utility of G minus G1. Since we have the small good assumption, we can apply the moving knife procedure to allocate the remaining goods, that is G minus G1, and let B1 to Bn denote the allocation resulting from step 2. We make the following claim that the value of the bundle obtained from the moving knife procedure is at least Li over 2n. The proof is simple. By the moving knife lemma, we know that the value obtained for a bundle from the moving knife procedure is at least a 2n approximation of the goods that we started out with. And here this set was G minus G1. Since the size of G1 is at most n, by definition of Li, since it is the minimum over all such removal of n goods, the value of G minus G1 is at least Li, and hence the value of Bi is at least Li over 2n for all the agents. Now we are ready to show that the Nash social welfare subadditive algorithm 1 is an 8n approximation for subadditive utilities. The final bundle obtained is the combination of the goods obtained from the moving knife procedure and the good that was matched. Here pi denotes the good that was matched and bi the bundle obtained from the moving knife procedure. So the Nash social welfare of the final bundle is at least that of the right hand side, and this follows simply from the monotonicity of vi. The second inequality follows from the previous claim that we proved, which states that the value for the bundle obtained from the moving knife procedure is at least Li over 2n. And the third inequality follows from the definition of the max weight matching we were using, where the weights are exactly that of the LHS. And finally, the last inequality follows from the stitching lemma. This gives us the 8n approximation under the assumption that we obtain only small goods after the matching step. Now, to remove the assumption that the goods that remain after the matching step are all small goods, we add an additional step to our algorithm. The first step remains the same, just the same max weight matching using the modified weights. And again, G1 denotes the goods assigned in the step 1. Note that the size of G1 is at most n, and step 2 says that if there exists a good which gives a 2n approximation to the value of goods in G minus G1, then assign that good to the agent I and remove I from consideration. The importance of this step is that when you pick out these goods which are sort of high valued, all that remains will be small valued, and then you can pass it on to the moving knife procedure to obtain the required approximation guarantee. Let G2 denote the goods assigned in step 2, and note again that this matching also would be of size at most n. Now, using the moving knife procedure, we can allocate the remaining goods, that is G minus G1 union G2, to obtain the final bundle, which is Bi union pi I. This is our final algorithm, and the previous approximation guarantee extend to give us an order and approximation for maximizing the net social welfare under subadditive valuations. Note that the approximation guarantees we give also hold for maximizing the weighted version of the net social welfare problem. We also give a square root m approximation combining the results of root A with that of ours. To conclude, let's revisit our results again. For subadditive utilities, we provide an order and approximation algorithm for net social welfare, and with minor modifications, our techniques extend to give an order and approximation for p-mean welfare for any p at most 1. We also show that the order n is tight for subadditive utilities by showing that it requires exponentially many value queries to improve the approximation even by an epsilon factor. We do this by providing an unconditional query-based lower bound. Here we list out a few open questions that we propose. Can the order and approximation for submodular NSW problem be improved? We know that our techniques won't extend to obtain a log n approximation for submodular valuations, and a new approach is required. Another question is whether using a demand oracle model would bypass the lower bound for value oracles. Also, what would be the best approximation possible for the net social welfare problem in the presence of strategic agents under submodular or subadditive valuations? With that, I conclude my talk. Thank you.